I do wish I could be in Montreal, beautiful city, visiting you all, but you know, happy to do this over Zoom. And again, I very much appreciate the invitation. So yeah, I'm going to talk about some joint work with Richard Melrose that has to do with this notion of bigerbes, which are sort of a notion of higher gerbes. I don't assume that everybody knows what gerbes are, so I'll spend a bit of time talking about that before jumping into this. But I'll talk about what bigerbes are and give some applications. Focus my pointer here. There we go. So here's the executive summary version. The idea with gerbes is that they're supposed to be something that lives in analogy to line bundles. So if we think about line bundles and their relationship to degree 2 integer cohomology, whatever that relationship is, that's supposed to be reflected in the relationship between gerbes and integer H3 cohomology. And then bigerbes, or kind of a version of higher gerbes, 2 gerbes, that have the same relationship with degree 4 cohomology, and so on. And then there are higher and higher versions of these. There's versions of these that will exist for every n, but I'll focus on the case of bigerbes for today, degree 4 cohomology. So what do I mean by this relationship? What is this relationship? They're meant to be geometric objects in some sense that represent and are classified by integer cohomology. And you know, I guess I'm using the term geometric in kind of a loose sense. Basically, everything I'm going to talk about today is in basically just the topological category. I'm not going to make use of much geometric structure. So, I mean, basically just a category of sort of reasonable spaces that you would encounter in like algebraic topology, for example. But still geometric in the sense that of sort of line bundles and some kind of objects that, you know, yeah, play a role in various geometric applications. And one theme that's going to come up over and over again is the triviality, or in particular the non-triviality of these objects corresponds to some kind of obstruction problem. Right, so just to review, just to sort of start, let's just review the situation for line bundles. So we have a complex line bundle over a space, and throughout we could switch between using complex line bundles and of course, you know, principal bundles with structure group C star or T. I'll use T consistently for the circle group. And yeah, so we'll freely interchange between those two things. But if we have a complex line bundle, of course, it has a characteristic class, the first Chern class in degree 2 integer cohomology, and that has a bunch of properties. So it's natural with respect to pullback. So we have a notion of pullback for line bundles, and that intertwines the pullback in cohomology. The Chern class is additive. So if we take the tensor product of line bundles, the Chern class is add. A Chern class is trivial if and only if L is trivial as a line bundle. And so therefore, you know, combined with the additivity property, we also see then that the Chern class of the inverse of a line bundle is the negative of the Chern class of the line bundle. And they're classified up to isomorphism, you know, again, sort of related to these previous two properties, that if two line bundles have the same Chern class, then they're necessarily isomorphic as line bundles. And then finally, a universality statement, which is that not just does every line bundle have a class, but every class has a line bundle, right? So every class in H2 corresponds to some equivalence class of complex line bundles. So if you like, this is kind of a geometrization of H2, this nice sort of category of objects that live over X that are represented naturally by H2 cohomology. And then the obstruction problem is fairly simple. In this case, of course, the obstruction, the non-triviality of a line bundle is just the obstruction to, well, it's the obstruction to triviality, right? So the obstruction to the existence of a global non-vanishing section of the line bundle, or if we're using the principal bundle language, just a global section, period. All right, so hopefully that's all familiar. But I wanted to highlight these properties because we're going to see those again reflected when we talk about gerbes and when we talk about bigerbes. So on to gerbes. Again, gerbes are supposed to be to H3 what line bundles are to H2. And there's various versions of the notion of gerbes that go back, I think, or the first version goes back to Giraud, and there's versions due to Berlinski. There's a version of gerbes due to Hitchin and Chatterjee. But what I'll talk about today is a version due to Murray, which is in some sense the most, I think, kind of concrete and geometric, which is the notion of bundle gerbes. So according to Murray and his paper from '96, a bundle gerbe on a space X, so it's 3 pieces of data, X is the space that we want to represent the cohomology of. So the first piece of data is a space that sits over X, a space that we'll call Y, with a map back to X, and this map is required to be locally split. And that just means that it's surjective, so continuous surjection that admits local sections. So in typical instances, this is a fiber bundle. That's an example of a locally split map. But there's also instances where you might want to consider something that is more general than a fiber bundle. So an example of a locally split map, which is not a fiber bundle, is if you fix an open cover of X, and then you take Y to be the disjoint union of all those sets in the open cover. And the map back to X is just the inclusion map on each component. So that's not a fiber bundle, but it is locally split, right? It surjects onto X, and then of course it has local sections because on each open set, you can identify it with the component sort of upstairs. And actually, if you do Gerbes with those kinds of locally split maps, you essentially recover the definition of Hitchin and Chatterjee. Right, so that's the first piece of data, this locally split map over X. And then on top of that, or really on top of the fiber square of that, so we're going to take the fiber product of Y with itself, Y cross Y over X, so just pairs of points in Y that sit over the same base point in X, which I'm going to denote by Y bracket 2 consistently. So I'll just call that the fiber square. On top of that space, we're going to put a complex line bundle, or again, a principal bundle, as according to preference. And this line bundle is then to be equipped with an associative product. So if we look at the fiber of the line bundle over a pair of points, over a pair Y1, Y2, remember these sit over the same base point in X, and then another element of the fiber of L over Y2, Y3, we're supposed to be able to sort of multiply those together and get an element of the fiber of L over Y1, Y3, right? Where Y1, Y2, Y3, these are triples of points now that all sit over the same base point in X. So we have some kind of product in this sense that multiplies things in slightly different fibers of the line bundle over Y squared. And this is required to be associative. So just associative means sort of the obvious thing. If I've got 4 points, Y1, Y2, Y3, Y4, all sitting over the same point in X, then I can look at these fibers, fiber over Y1, Y2, over Y2, Y3, and over Y3, Y4. And if I have elements, 3 elements, one from each of those, then there's 2 ways to multiply them up to get an element of Y1, Y4. And associativity means that those give you the same thing. One way to formulate this, one way to state this kind of data is we could say that Y has the structure of a C star groupoid over X. I'm not going to emphasize this point of view necessarily, but if you like this, let me just explain it for the moment. So if we think about the fiber of Y over a fixed point in X, the points in that fiber of Y form the objects of this groupoid, right? So then pairs of those objects, pairs of things that sit over the same point in X, those are things that we could try to move between in the groupoid. And then the idea is that L, maybe especially if we're viewing L as a principal C star bundle, represents the homomorphisms in this groupoid between Y1 and Y2. It's the Hom space from Y1 to Y2. And so that's just basically required to be a C star for every point. So it's a groupoid where each Hom set has the structure of the group C star. And then just to say it's a groupoid over X just means that this is all kind of fibered over X for some topological space. So if you like that version of things, that makes contact with Berlinski's notion of Gerbes, which are sheaves of groupoids, and also makes contact with Giraud's kind of original definition of Gerbes. But again, I'm not going to emphasize the groupoid aspect of this. I'm going to emphasize more the kind of bundle picture. And I should say also, please feel free to interrupt me and ask questions at any point. This is, I'm happy to go on diversions as people like. Right, so here's again the setup. We've got X, Y sitting over X, Y squared has 2 maps back to Y, and we've got a line bundle sitting over Y squared. And so associated to this setup, there's a way to associate a characteristic class, a characteristic cohomology class called the Demier-Duidie class. And it's a class in integer H3, so integer degree 3 cohomology of X. And it has properties exactly similar to the Chern class of a line bundle. So there's a naturality property. Bundle gerbes have a natural notion of pullback. So if I've got a space x prime and a map to x, I can pull back all of this data over x prime. I can pull back y over x prime. So I can pull back y squared over x prime, and I can pull back the bundle upstairs over all of that. And so that gives me a bundle gerb sitting over x prime. And the pullback intertwines the pullback on cohomology. And then again, there's a natural notion of products. I can take the product of two bundle gerbs, which is basically just the fiber product of the y's, and then upstairs the tensor product of the line bundles. And this characteristic class is additive with respect to that operation, and also respects inverses, where the inverse, the easiest way to write down the inverse of a bundle gerb is just to take the inverse of the line bundle at the top level. And then the characteristic class is minus the characteristic class of the original one. And a notion of triviality. This is maybe not the first thing that you might think. You might think the bundle gerb is trivial if the line bundle is trivial. But there's actually a slightly weaker notion that turns out to be correct. So we'll say a trivialization of a bundle gerb is a line bundle that sits over y, right? So L sits over y squared. If we have a line bundle Q that sits over y, that has the property that when we take the alternating product of the pullbacks of y, so there's two maps here from y squared to y, the two projections. If we pull it back two ways and take the tensor product of one with the inverse of another, and we'll call that kind of the differential of Q. I'll expand on that a little bit later. If L is isomorphic to such a line bundle, we'll call that a trivial bundle gerb. And we'll call that actually a trivialization of a bundle gerb, and then a bundle gerb is trivial if such a trivialization exists. And that happens if and only if this characteristic class vanishes. All right, so it's a slightly weaker notion than triviality of L as a line bundle over y squared. If L is trivial, then you can take Q to be the trivial bundle, and this all works. But there are also instances where L is trivial as a bundle gerb, but not trivial as a line bundle. Then there's a corresponding notion of classification. There's a notion of, there's actually a few different notions of isomorphism for bundle gerbs. But the slightly weaker one that we want here is some notion of stable isomorphism that's due to Murray and Stevenson in 2000. It's basically the statement that the tensor product of the two bundle gerbs is trivial. And then if we make that definition, then of course two bundle gerbs that have the same characteristic class are stably isomorphic, and conversely. Right, so those are, again, supposed to mirror those same properties of complex line bundles with respect to H2. They were represented by this now degree 3 cohomology class with these natural properties. Right, so what can you do with them? What's the point?
Chris,
yes.
About this triviality, naively, I would expect maybe it will be L prime inverse that you have to put when you take the tensor product. If you think in terms of line bundles, you would have to put the...
Oh, yeah, you're sorry, yeah. Yeah, you're right. That's a misprint. That should be L tensor L prime inverse. Yeah. Because that will happen if and only if they have the same characteristic class. Thank you for that. Yeah, good catch. Right, so what can you do with bundle gerbs? One sort of reasonable application of bundle gerbs has to do with the problem of lifting the structure group of a principal bundle to a central extension of that structure group by the circle. So let's suppose we've got a topological group G, and it has some central extension by the circle, or again, C star, doesn't really matter, but let's say the circle. So we've got this central extension, this short exact sequence. In particular, if we look at G hat, the central extension, over G, and we just forget the group structure for a second, we can view this as a circle bundle. Right? Central extension is, among other things, just a circle bundle. And so then if we've got now a space with a principal G bundle over it, let's call E the total space of the principal G bundle, then if we look at the square of E with itself, right, so pairs of points in E that sit over the same point in the base, using the principal bundle structure, there's a natural difference map that maps from E squared to G, right? So this just says if y0 and y1 are 2 points over the same point in the base, there's a unique element of the group that translates y0 to y1, right? So we call this the kind of difference map. G is essentially like the difference of y1 and y0. Right, so then we take E to be the fiber space over X for the definition of the bundle gerb. So we're gonna put a circle bundle over E squared. And how do we get that circle bundle? Well, we just take this difference map from E squared to G. We're viewing the central extension of G as a circle bundle over G, so we can just pull that back. So we pull back G hat to E squared viewed as a circle bundle. And so we have the data of a bundle gerb, and the only thing missing is to check that this has a gerb product. And it does, because now we can remember that G hat is in fact a group that sits over the group structure of G. So the gerb, there's a natural gerb product on this thing that comes from the group structure of G hat. So we've got a bundle gerb. So again, here's the data just summarized up here. And then, I think one of the main applications of bundle gerbs as originally envisioned by Murray is this result that a trivialization of this bundle gerb is the same thing as a lift of the original principal bundle E to a principal G hat bundle, right? So if we're asking the question, like I've got this structure group G for X in this principal bundle, can I refine this structure group or lift this structure group to the central extension? That problem is exactly equivalent to the question of whether this bundle gerb is trivial in the sense of bundle gerbs. And so, of course, that's answered by whether this characteristic class vanishes. And so we get a characteristic class in H3 of X, which then represents the obstruction to this lifting problem. And just as a familiar example, right, if we take X, let's say, to be an oriented Riemannian manifold, so we view its principal frame bundle as a principal bundle with structure group SON. Well, there are circle central extensions of SON, which are the spin C. So the spin C group is a circle central extension of SON, and so this encodes the question of whether we can find a spin C structure on a given oriented Riemannian manifold. And of course, it's not a surprise, perhaps, that the Demia-Duodee class of this bundle gerb, if you do this lifting bundle gerb in this instance, that turns out to be the integral Stiefel-Whitney class, the integral third Stiefel-Whitney class of the manifold itself, right, which is sort of well known to be the obstruction to admitting a spin C structure. So that's an example of an application of bundle gerbs in the classical sense. I'll give one more example of bundle gerbs before going on. Another thing that we can look at is the based path space over X. So let's just fix a base point in X and then just look at the space of all based paths. So starting at the base point at 0 and then ending somewhere else at point 1. And we'll take the evaluation map at the far end point, the evaluation map at 1, back to X. So if our space is locally contractible, which is a quite mild condition, then this becomes a locally split map. And this turns out to be universal in the sense that every integer 3 class on X can be represented by a bundle gerb where the fiber space is this path space. And so this goes already back to Berlinski in his book, and also appears in Murray's paper on bundle gerbs. Maybe one little comment here. You can ask the general question of, suppose I have a 3 class on X, for what spaces Y can I build a bundle gerb with that given 3 class? And as far as I know, that question isn't answered in the literature. It was a little bit surprising that I wasn't able to find that in the literature, but there is a theorem. You can show that there's a condition that you can do this if and only if the 3 class that you want to represent on X pulls back to vanish on Y. So if you've got a given locally split map from Y to X, you can use Y to represent a bundle gerb for a given 3 class if and only if that class pulls back trivially to Y. And so, of course, the path space is contractible. Every 3 class pulls back trivially to the path space, so you can represent every 3 class by a bundle gerb. Now, I want to give kind of a different point of view on this, because, of course, so the bundle gerb, right, where we have a line bundle over the fiber square of our space. So what is that in this instance? We have pairs of based paths that have the same endpoint in X. So of course we can identify that with the based loop space, right? So if I've got two paths that start at the base point and end at the same point, gamma 1 and gamma 2, well, we can just reverse gamma 2 and concatenate those paths together, and we get a based continuous loop. I'll call that L12. And conversely, right? Anytime we have a based loop, we can split it at the midpoint of the loop and reverse the second half and view it as two paths meeting at the same point. And again, just to emphasize, we're using just continuous things here. It's a little bit more complicated if we want to use smooth paths and loops, although it can be done. So from this point of view, right, the data of a bundle gerb involves a certain line bundle that sits over loop space. And of course, a line bundle has a Chern class, as we discussed, right? So we've got this line bundle is represented by a degree 2 cohomology class on the loop space. On the other hand, this bundle gerb is supposed to be representing a degree 3 cohomology class downstairs. So, you know, it's natural to ask, how are these classes related? We got a degree 3 cohomology class downstairs and degree 2 cohomology class upstairs on the loop space. And you might guess the answer. There's a well-known transgression map in cohomology that passes from the cohomology of a space to cohomology of degree 1 lower on the loop space. Right, so this is maybe how to write it down in general. If you take the circle times the loop, there's a natural evaluation map to the space X, which is just evaluating the loop at each given point on the circle. So we can pull back classes on X by this evaluation map to this product, and then we can take the cap product with the fundamental class of the circle to sort of kill off this factor, and then we land in the cohomology of the loop space. And since the cap product, the fundamental class of the circle is degree 1, we lower the degree by 1, right? So this composite map is the transgression map, the transgression homomorphism in cohomology. And it's true that the Chern class of the line bundle that sits over the loop space, if we view the loop space as the total space supporting this bundle gerb, it's the image under this transgression map. So it's just the transgression of the characteristic class of the bundle gerb downstairs. But some information is lost, right? If we just think of this as a line bundle, we're forgetting the extra data of the gerb, which is this gerb product. And that's related to the fact that this transgression map in cohomology, it's neither injective nor surjective in general. This is, you know, it's not an isomorphism for sure. And so, yeah, it's related to the fact that this map in cohomology is not encoding the gerb product on the line bundle. This gerb product on the line bundle over the loop space is sort of known by another name. It appeared in the work of Stolz and Teichner going back to 2004, not in reference to gerbs. It sort of appeared on its own in a different context, but it turns out to be just exactly equivalent to the sort of data of a gerb. So, right, so viewing pairs of paths as loops in this way, we have what's sometimes called the fusion product on loop space, which is to say, if we have 3 loops on a space that have this configuration, they basically come from 3 paths that all have the same endpoint, where we identify the first 2 paths as the first loop, the second 2 paths as the second loop, and then the first and third or outermost 2 paths as the third loop. We say that this loop is the sort of fusion of these first 2 loops. And then as defined by Stolz and Teichner and Waldorf a little bit later, you can talk about the notion of a fusion bundle or a fusion line bundle on loop space, which is just to say that you have a product just like the gerb product. I mean, it's exactly the data of the gerb product if you just unpack it in this way. So just to make contact with this earlier literature, a gerb using the path space for its fiber space, a bundle gerb using the path space for its fiber space, is equivalent to what was previously called a fusion line bundle over loop space. And sorry, I keep moving my mouse so this little thing appears, but once that disappears, this tells us in particular that we have a bijection because we can represent every degree 3 cohomology class on X by a bundle gerb using the path space, and then view that as a fusion line bundle. This gives us a bijection between degree 3 cohomology on X and fusion line bundles upstairs. So if we sort of remember the fusion or this gerb product, then there's a bijection. Whereas this transgression map is sort of forgetting some information. Just two remarks before I go on. It's possible to build this notion of fusion that I previously talked about in the sense of line bundles actually just into a cohomology theory itself on loop space. You can talk about fusion cohomology on loop space, and then you can promote this transgression map to actually an isomorphism. The statement is that there's actually an isomorphism between integer cohomology on X and fusion integer cohomology on the loop space degree 1 lower. Actually, I think I gave a talk about that here at UCAM a couple of years ago. And then the other remark is that if you don't like using the base loop space for various reasons, you might prefer to use the free loop space. It's also possible to use the free loop space and make analogous statements. There's an additional condition that you need to build in the free loop space, but that can be done. I won't go into that, but right. So just to kind of tee up the notion of higher gerbs, let me give one more way to think about this bundle gerb construction. So going back to our locally split map y over x, we can form its successive fiber products with itself over x. So the fiber square, the fiber cube, and so on. These all come with maps back to the previous space, just the maps that forget the factors. If we look at just the y's here, these form the data of what's called a simplicial space over x, right? So the y's, this just means that we have, for each natural number, we have a space, and then we've got maps back between those spaces that satisfy the face relations that simplices do, right? So these projection maps satisfy these simplicial relations, like this is 1, for example, just the usual relations that the faces of an n-simplex have with respect to one another. There's other data actually of the degeneracy maps going the other way, but we're not going to make use of that. And then to say that this is a simplicial space over x just is to say that all of these maps admit a common map to x. Right, and so then in this language, the structure of a bundle gerb, which is the line bundle sitting over y2 here, well, actually, yeah, anytime we have a line bundle sitting over any one of these, because we have pullbacks for line bundles, we have products, we have inverses, and we have the notion of trivializations for line bundles, we can define this kind of delta L, right? So anytime we have a line bundle over any one of these, we can pull it back by all of the projection maps to the next space up and take the alternating tensor product of those things. If you do that twice, you see that the same factors appear in opposite pairs, and so they canonically cancel. So if you do this twice for a line bundle, you get that delta squared of L is canonically trivial. So this is some kind of differential on line bundles associated to a simplicial space. So in this language, we can say that a bundle gerb is what's called a simplicial line bundle, as defined by Berlinski and McLaughlin back in '94, meaning that we've got a simplicial space, we put a line bundle over y2, and then we equip that with a trivialization of delta L over y3, such that that trivialization of delta L induces the canonical trivialization over delta squared of L. So to say that delta of L has a trivialization, if you sit down and check, just write it down, that's completely equivalent to the existence of this gerb product. And then the statement that that trivialization coincides with the canonical trivialization over here encodes the associativity of the gerb product. So this is just the same data in another language. And then in this language, the trivialization of the bundle gerb is the statement that L is delta of some Q that sits over Y.
Chris, does
Yep.
delta L admit a trivialization always, or?
No, so if you put an arbitrary line bundle over Y squared, delta of L might not admit a trivialization. So yeah, part of the data of a bundle gerb is that it is trivial and you equip it with a given trivialization.
Okay, but then nevertheless, delta 2 of L will always be canonically trivial.
Yes, delta 2 of L is always canonically trivial no matter what you do. Yeah, good. So this is just, again, a repackaging of the data of a bundle gerb in this slightly different language. But this tees up, so yeah, this this forms the basis for one direction for how you might try to formulate higher notions of gerbes, right? So we've got line bundles that are associated to H2, gerbes that are associated to H3. So now we'd like to say what's associated to H4. So I'll first give you a notion of two gerbes that, there's various notions of two gerbes that have been written down by various authors. I'll explain one that was written down by Danny Stevenson in 2004, a student of Murray. This begins with the observation that in this previous construction here, right, all that we needed to formulate this stuff was the notion of pullbacks, products, inverses, and trivializations, right? Line bundles have pullbacks, products, trivializations, and inverses. And so we can write these conditions down on this simplicial space coming from a locally split map over X. Well, bundle gerbes themselves have those operations, right? We can pull back bundle gerbes, we can take products of bundle gerbes, we can take inverses, and we have a notion of trivializations. So we can just try to play the same game again. So this is Stevenson's notion of a bundle chew gerbe, which is to say that it's a simplicial bundle gerbe. So let's start with a locally split map Y over X, and we form this, again, sequence of all its fiber products going off to the right. I've stopped drawing all the arrows. And then instead of putting a line bundle over Y2, let's put a bundle gerbe over Y2. So we've got, a space Z sitting over Y2, and then over Z squared sitting over Y2, we've got a line bundle sitting over that, right? So all the data of a bundle gerbe that I'll just denote by this blackboard bold L sits over Y2. And then, so we'll say that should admit a trivialization when we apply the product of its pullbacks over Y3. So this delta of L we can define over Y3 and say that should admit a trivialization. And then it starts to get a little complicated because we want to compare that to some kind of canonical trivialization of delta 2L over Y to the fourth. But in order to do that, we need this notion of two morphisms. I didn't tell you that bundle gerbes have some notion of two morphisms. That relates the induced trivialization to this canonical trivialization over here. And then you also need some kind of coherency condition on pulled back two morphisms over Y5. So this thing kind of bleeds off to the right a little bit, and it gets kind of complicated and scary. But you can do it. You can write it down, and you get some reasonable notion of a two gerbe, and it has the benefit that it has a if you've got all this data and you write it down, you get a well-defined characteristic class in degree 4 cohomology, and it has the expected properties. It's natural with respect to pullback. There's products and inverses and sort of all the usual stuff. But I would say it has some drawbacks. One complaint that you can level at this construction is that the roles of Y and Z are very kind of asymmetric in this picture, right? So Y sits over X, but Z is kind of very far removed from X. Z is the fiber space of the bundle gerbe sitting over Y squared. So it's kind of very far away from X. You can't like interchange Y and Z. And if you want to keep going to higher and higher, I think more seriously, if you want to keep going to higher and higher versions of bundle gerbes, if you want to represent degree 5 cohomology and above, you can keep trying to play this game, but it gets worse every time. Every time you go up, you get higher and more complicated coherency conditions that have to be satisfied over higher and higher products of Y, if you like, right? And you have to incorporate higher and higher categorical concepts, right? You go from 2 morphisms, then you'll have 3 morphisms, and so it just starts to get kind of wild and complicated. And if you like higher category theory, maybe that's your thing. But the point of this talk is that there's another way that kind of avoids all of that. So this is the point in this infomercial where it turns from black and white into color, and we say there's a better way to do this. So the claim is that here's another definition of kind of 2 gerbes that we call bigerbes that avoids both of those previous drawbacks. So it starts with the following setup. We've got X, which is the space that we want to represent degree 4 cohomology over. And we're going to start with what we call a locally split square. So this is just a diagram like this where Y and Z are spaces over X. The maps here are both locally split. And then we've got a space W that maps to Y and Z, commuting with the maps to X. Anytime you have this situation, there's a natural map from W into the fiber product of Y and Z, and we require that that's also locally split. As a consequence, all of these four maps are locally split. So we call that a locally split square. In many instances, you can just take W to be the fiber product of Y and Z. We'll see that in some examples, but it's useful to have it be more general. So then starting with this square, in which we can see that Y and Z have exactly the same relationship to X, right? They appear on the same footing. We can start filling out this diagram by fiber products, right? So we can take fiber products of Y with itself over X going off to the right, fiber products of Z with itself over X going up. And then we can take fiber products of W with itself over Y going up here, and then fiber products of W with itself over Z going off to the right here. And you can easily see that there's maps going from right to left up here, and from up to down here and here. And so you can keep filling it out by fiber products, right? So if we take this W12 space and we take fiber product of itself over Z squared, we get a space here. That turns out to actually be the same thing as taking this space, W21, the fiber product of itself, over Y squared. So all of these spaces are kind of well defined if you view them as fiber products vertically or horizontally. They turn out to be the same thing. So you just fill out this diagram by fiber products and you start enumerating it with two indices. And then just like we did before, where we just looked at the Y's and we sort of forgot about X for a second, if we just look at the W's, I guess I can't highlight just the W's. If we look at just the W's, all the spaces that are indexed by W with two integers, that forms the data of what's called a bisimplicial space. So it's just indexed by two natural numbers. And we've got these maps going down to the left that satisfy simplicial relations in two different directions. And so in particular, if we put line bundles in any one of these spaces, we've got two differentials. We can take a differential in the vertical direction or a differential in the horizontal direction. So yeah, just to kind of make contact with the notion of two gerbes before, we could try to do the kind of two gerb thing in two different ways here, right? So we got Y along the bottom. If we wanted to put a bundle gerb over Y, well, we could let W21 be the space admitting the bundle gerb. And so if we take the fiber product of that with itself, we'd be working on this space. We'd put a line bundle over W22 for a two gerb. And the advantage now is that we can do this in this is the same space viewed in two different ways, right? So we could also view this as a bundle two gerb using Z sitting over X or using Y sitting over X. So that's the data that we're going to equip. A bundle bigerb, starting with this locally split square, is going to be a line bundle that sits over W22. And it's bisimplicial in the following sense. So we've got these two different differentials. So we can look at delta 1 of L going to the right. We demand that delta 1 of L and delta 2 of L be equipped with trivializations. This is kind of the gerb product condition, such that they induce the canonical trivializations of delta 1 squared and delta 2 squared of L. And also that these two trivializations induce the same trivialization of delta 1, delta 2 L. So it's a very natural condition if you write down this square. So that's it. That's the definition of a bundle bigerb. It's a little bit involved, but it's fairly natural and fairly combinatorial. I claim, I won't go into the details, but I claim that products, inverses, and pullbacks are all straightforward to define. So if we've got a map from another space into X, we can just pull back the whole square over X, take fiber products again. So we can pull back all the data, and that's the pullback of a bigerb. Products, you can just take fiber products of everything, all the data over X, and then the tensor product of the line bundles, that's a product. Inverses, you can just take the inverse of the line bundle. So these are all straightforward. And a trivialization in this sense, the right notion of the trivialization turns out to be that if L is isomorphic to a tensor product of line bundles, delta 1 of Q1 and delta 2 of Q2. So if there's a line bundle coming from below and a line bundle coming from the right whose tensor product is isomorphic to L, we'll say it's trivial, and that data will be a trivialization. Right, and so then the theorem is that this has all the right properties, right? So you can associate to this a well-defined characteristic class in degree 4, and we just call G for gerb, I guess, and it has the properties that you expect. It's natural with respect to pullbacks, additive with respect to products, and the inverses have the opposite characteristic class. It's trivial only if and only if the Bigerbe admits a trivialization in this sense, and sort of a classification statement that, you know, two bundle Bigerbes have the same characteristic class if and only if they are stably isomorphic. Stable isomorphism is essentially the same thing as their tensor product of the one with the inverse of the other being trivial again. And also, there's also a theorem, you can ask the same question. I have a given 4 class. When can I use a given locally split square to represent this 4 class by a Bigerbe? There's a theorem that tells you a condition on W, Z, and Y, and the maps to support a Bigerbe. So the benefits of this are there's no higher category stuff. We don't have to talk about two morphisms or this coherency condition over Y5 or whatever. And the claim is that this also generalizes in a very straightforward manner to higher degree. I won't give you the definition, but you are now well equipped to just write down the definition. The one that you will write down will end up being the correct one. So instead of starting with a locally split square, you start with a locally split cube or n cube, right? It's the thing that you think it is if you write down the analogous description. And then, you know, fill that out by fiber products and go up 2 steps kind of diagonally, put a line bundle over there. You now have however many differentials you have. It should have trivializations in all those directions in a compatible sense. That's a bundle. That's a bundle multi-gerbe. And the claim is that you can play this same game and they have a characteristic class in the appropriate degree with all these properties. So that's all well and good. It's you know, fine to write down a nice definition of something, but you know, if there are no interesting ones, who cares, right? So are there any applications? Can we actually do anything with this? So let me give at least one interesting application here that has to do with the, sorry, I think I'm running out of time, the Whitehead tower for the orthogonal group. So let me just tee that up really quickly. If we think about the orthogonal group, ON, SON, spin n, what are we doing here? ON is, you know, has multiple components, right? Pi 0 is Z2, has 2 components. If we pass to the connected component of the identity, now SON is connected, but it's not simply connected. Pi 1 is Z2. If we pass to the Z2 cover, we get the spin group that kills off Pi 1. And incidentally, Pi 2 is also vanishing, but it has non-trivial Pi 3. So we can ask, now is there a group that sits over all of this that kills off Pi 3? And that thing's called the string group. It's a 3-connected topological group that sits over spin in this diagram. It's not a finite cover. In fact, it's not even a finite dimensional Lie group, but it is a topological group. And these are associated with kind of you know, structural conditions on a Riemannian manifold, right? So to reduce the structure group of a Riemannian manifold to SON is to put an orientation on it. To enhance that structure group further to spin is to put a spin structure on it. So both of those things are obstructed by cohomology classes, and then if the obstruction vanishes, they're classified by cohomology groups. And the same thing is true of so-called string structures. So we say that a manifold is a string structure if you can enhance the structure group to this string group, and that has a degree 4 obstruction class, which is the first Pontryagin class of the manifold. And if that vanishes, then string classes are in bijection with H3 of X. Right, and there's a degree lowering sort of transgression relationship between these structures on X and structures up on the loop space related to the transgression relationship that we talked about before. So for example, if we just have, if X is oriented, so we're talking about SON, well, loops on SON are not connected, of course, because SON is not simply connected. And so loops are picking up that non-simply connected thing. If you are able to reduce the loop SON structure, I should say, if you just loop everything, then the loops on the total space of the principal bundle over X form a loop group principal bundle over the loop space of X. A reduction of that group to the connected component of the identity, which is exactly those loops that lift to loops in spin, can be regarded as an orientation on the loop space, or we'll call it a loop orientation. And so by transgression, we see that if X admits a spin structure, then the loop space admits an orientation, but not conversely, because again, we're forgetting some kind of structure here. And it's the fusion structure, right? So this is one of the reasons for Stolz and Teichner to discuss fusion in the first place. Turns out that there is a bijection between spin structures on X and not just any old orientations on the loop space, but fusion orientations on the loop space if we incorporate this fusion product somehow. Going 1 degree higher, we can talk about what are string structures on X supposed to be related to. Well, they're related to spin structures on the loop space, where that means the following thing. Loop groups are well known to admit central extensions by the circle. In particular, there's a universal one, let's say for loop spin, that's determined by a generator of H3, which is just Z. So we'll say that a loop spin structure up on the loop space is the enhancement of the structure group from loop spin to this central extension of loop spin. The obstruction to that is the transgression of this 4 class on X that is the obstruction to the string structures on X. So that's a degree 3 class on the loop space. So again, we get this statement that if X is a string manifold, if it admits a string structure, then the loop space admits a loop spin structure. But not conversely, it's not if and only if. We have to incorporate fusion somehow. And this gets a little bit more complicated. There is some existing literature on the relationship between these two things, incorporating fusion structures or things related to fusion structures. Earlier work of myself and Richard Melrose, work of Waldorf, Stolz and Teichner. There's also some discussion of 2 gerbes downstairs on X that are related to the spin structure on the loop space due to Berlinski and McLaughlin, and this paper by Carey, Johnson, Murray, Stevenson, and Wang. But all of these pictures are still a little bit complicated and don't give you a completely clear picture of the relationship between string structures on X and loop spin structures upstairs. And the claim is that there's a bigerbe that gives a really clear picture of all of this. So we've got X downstairs, and the locally split square we're going to take has the structure group of the principal bundle of X sitting on top of X in one direction, and the path space of X going off in the other direction. And then the space sitting at the corner here is the path in E. So this forms a locally split square. We fill it out by fiber products. And once again, the fiber square of the path spaces, we realize that we can associate those with the loop space again. And so going off horizontally, we have spaces, paths, and then loops in those spaces. And vertically, all of these things are principal bundles. We've got a space downstairs, the total space of a principal bundle over it. In this case, like a spin principal bundle. In this case, a loop spin principal bundle. And then these spaces upstairs are just the fiber products of those principal bundles with themselves. So again, there's a difference map from this double space of this principal bundle, the loop spin principal bundle, to the loop group, loop spin. And that has a central extension over it. And so we can pull that back by the difference map. So this is a circle bundle. We could view it as a line bundle or a circle bundle if we like. So if we pull that back to this space, that is the data that we need for a bundle bigerbe. And it is a bundle bigerbe. It has these 2 sort of simplicial conditions. So the theorem here is that this determines a bigerbe, has the characteristic class that we want, this characteristic class that obstructs string structures downstairs. Trivializations of this bigerbe are equivalent exactly to fusion loop spin structures. And so these are therefore in bijection with degree 3 cohomology in the case that it's unobstructed, and therefore with string structures on X. Just 2 comments. Simpliciality in the vertical direction, or the gerbe product in the vertical direction, comes from this thing viewed just as a lifting bundle gerbe. This is just a lifting bundle gerbe construction on the loop space, because we've got a group and a central extension of the group by the circle. And then the simpliciality in the horizontal direction is encoding this fusion or the gerbe product condition. So since I'm out of time, there are 2 more applications that I won't go through, but I'll just say very briefly that bigerbes, you can also use them in a cute way to represent cup products. So if you have a degree 4 class that's the product of 2 degree 2 classes, then there's a canonical way to construct a bigerbe associated to that. Or if you've got a 3 class cup, a 1 class, you can construct a bigerbe out of a bundle gerbe associated to the 3 class and then a Z cover associated to the 1 class. But I won't go through those in detail in the interest of time. So let me just skip to the end. Thank you. Here's the bibliography, all the papers that I referenced, and then this one in red is the main paper that all of this stuff is in. It's on the archive and will appear in algebraic and geometric topology soon. So thank you.
Thank you very much for your very nice talk. Are there any questions or remarks?
Yeah, I do have a question. So are there notion of connection or curvature for these objects?
Yeah, that's definitely a next step. I definitely want to. There should be, right? I mean, there's notions of connections and curvature for Gerbes. It's an important part of the story for Gerbes, as it is for line bundles. And various versions of higher Gerbes have been written down with connections. So yeah, there should be a notion of connection and curvature, and probably another thing that's associated to all this setup that we haven't sat down and tried to develop yet. But yes, that's a good outstanding question.
Is there also with the double complex involved? I was curious. Is there? Do you use spectral sequences somehow to obtain some of the results? Oh.
A little bit, yeah. I mean, so it turned out to be actually fairly trivial. I didn't tell you how to define this characteristic class, but it turns out you can do it's a check cohomology construction. Basically, you work in check cohomology with all these spaces, and so for let's say the bigerbe, you have two differentials coming from the two different simplicial directions in the simplicial space, and you have a third differential that comes from the check differential, and so you actually have a triple complex. But what turns out to be the case, so if you look at check chains on all these spaces with these three differentials, the complexes that you get in the simplicial directions turn out to actually be exact. So the requiring that the maps are locally split turns out to give you the property that the associated differential on check cochains is exact. So in a certain sense, they are spectral sequences, but they all degenerate just immediately because one of the differentials is exact. So yeah, so you can do it in terms of spectral sequences. It's also just fairly simple diagram chasing that you can do explicitly using exactness. Yeah.
Okay, very good. Are there any other questions or remarks?
Yeah, I have a question. Thanks for the nice talk, Chris. I was wondering if there's any connection between these bigerbes and the Strominger system in heterotic string theory, where there's an equation that implies the cancellation of the Pontryagin class.
Oh, interesting.
If formalism can give any perspective on that.
I mean, I'm not familiar with that, so I can't comment on that directly. But I will say that this 4-class on X and associated string structures upstairs, those are related to things that are meant to be coming out of string theory. So, the context for this, like, what do you want to do with this loop spin structure up on loop space to lift from loop spin group to the central extension, is that there's supposed to be a Dirac operator on loop space that is, in this context, the analog of the Atiyah-Singer Dirac operator on a spin manifold, right? And sort of conjecturally or formally, the index of the associated Dirac operator on the loop space is supposed to be giving you this genus, the elliptic genus, or the Witten genus of a string manifold. And so there's this kind of analogous picture to, on a spin manifold, the Atiyah-Singer Dirac operator computes the A hat genus, and it's an integer because it's an index of an elliptic operator. Mm-hmm. So there's supposed to be a sort of a similar story that's going on the loop space with this Dirac operator that computes the Witten genus or various of these elliptic genera. And I think aspects of this are being worked on and not fully understood yet in a mathematical context, but that's definitely the background to this and part of the ongoing project with Melrose that I'm working on is trying to understand that picture.
Okay, thanks.
Actually, there is a relationship with the Strominger system. That would be probably, the development of curvature and connection, information, as asked Frederick in his first question, should help a lot.
Yeah.
That's, of course, very interesting.
Yeah, no, that's definitely an important part of this. I think one of the difficulties is that except in very special cases, most of the spaces involved are infinite dimensional. And so, you know, depending on how picky you are, you have to, you want to talk about connections and kind of a Deligne or de Rham cohomology theory, you have to think a little bit about regularity and what you mean by that on an infinite dimensional space. And yes, I'll say my collaborator has strong feelings about that. So that's yeah, one of the reasons for skipping it on the first instance and not worrying about connections.
Oh, I see. Okay, very good. Are there any other comments, remarks, questions from the audience? Okay, so I think it's time to thank Chris. So let's virtually thank him.
Thanks again. So yeah, pleasure to visit virtually.